Howdy. If you're watching this video, you probably have come out of your AP US exam. I hope things went well for you. We're going to be talking today about generators, and I want to start with a concept that's in your book that is an extension of Faraday's law of induction. So remember that our guiding principle for this entire chapter has been that the EMF that is generated by magnetic field is equal to
negative
Yeah, good. That's exactly it. That's a good job. Okay. And so what I'd like to do is I'd like to examine a conductor moving across through a magnetic field here, and we want to use this Faraday's law of induction to figure out exactly how much EMF is going to be generated as our conductor moves through here. Now, the way this is depicted is a little strange. They show a wire, but the wire is not necessary. So I want to start with a metal bar. Do this in different colors so you can see it. A metal bar. We're going to give that metal bar a length of L. Okay. And now we're going to drag that metal bar at a constant speed V through the magnetic field. When we do, actually, we're going to have to exert a force on it. That metal bar is not going to come at a constant speed for free, but it's going to require a force because we are moving charges through magnetic field lines. And when we do move charges through magnetic field lines, if we use our right-hand rule, you can stick your fingers out through the magnetic field, and you can put your thumb in the direction of velocity, and you can see that positive charge is going to be forced down this way, and negative charge is going to be forced up this way. Now, the positive charges are not going to move very much because they consist of the nuclei of the metal, right? Of the atoms of the metal, and those nuclei are large, massive. They're not going to move, but the electrons are very free to move, so they're going to move up. And as a result, we're going to get some charge separation. And we're going to end up with some minus here and some plus here. And you recall that we called this by a certain name. Do you remember? May not remember. I mentioned it. It's called the Hall effect. And I described it qualitatively in our notes previously, but now we're actually going to put some numbers to it by using Faraday's law of induction. Okay, so actually the analysis is fairly easy. If we move from here out to a position here, delta x, and we are moving at a constant speed, then the distance delta x that we move is just speed times time, or v delta t. That's what they show right here in the diagram. Okay. And as we are doing this, what we're doing is we're actually changing the area, so to speak, that is swept out by this metal bar as it goes. So if we think in terms of Faraday's law of induction, that the EMF generated is equal to negative n times change in flux over change in time, well, n here is just 1 because I don't have any coils of wire going in. I just have a single metal bar. And the change in flux over change in time is now not caused by a change in the magnetic field, but instead is caused by a change in the area that is swept by this metal bar. The area is increasing because I'm moving that metal through a larger thing. Let's examine that rectangle. If I look at initial and final, right here, so my bar moves from here to here, a distance of delta x. The bar has a length of L. Then, if I consider the initial area to be 0, essentially, because the bar hasn't moved at the initial state, then the final area is going to be L times delta x, which is equal to L times V times delta t. And because I'm sweeping the bar through the magnetic field right here, my area vector will be pointing straight out of the board. And the magnetic field is also pointing straight out of the board, with the result that the angle between those two is 0. And if I now put it all together and say that the EMF generated is equal to negative change in flux over change in time, where n here is 1, then that's going to be equal to the final flux minus the initial flux. The final flux is going to be field times area times cosine of the angle between. That's going to be B times LV delta T times the cosine of 0 degrees, which is circle, 1. Exactly. And the initial flux is 0. And would you look at that? The delta T's cancel out here, so that I get negative BLV. Now, usually we ignore the negative sign because we're only interested in the magnitude of that EMF that's generated. So we would usually write the equation like this: E is equal to BLV. And if we want to determine plus or minus signs, where the charge is going to be concentrated, then we are going to use our right-hand rule to do that, or really the left-hand rule.
So you can't see
It's not so much that, it's that we're looking at the magnitude.
Thank you for that.
Right. And magnitude is just the size without considering plus or minus. So this is our first concept, and that is that if we have a if we have a piece of metal moving through magnetic field, then we're going to generate an EMF that's equal to BLV. Now I want to put this up against other equations that we have generated using Faraday's law for other situations, just so we can compare and contrast them. Here what we were doing was taking and moving a piece of metal. In the previous situations, we actually changed the magnetic field. Remember that? We had like some kind of a loop. We turned on the magnetic field, we turned off the magnetic field, and we had the EMF generated as a result of that. And so if we had a loop and a changing field, then the EMF that we got was equal to negative times area of the field times change in field over change in time times the cosine of the angle between. And so here we see the contrast between changing field on the one hand and changing area on the other hand. Same principle, Faraday's law of induction, but now when we apply it to different situations, we end up with very different looking equations. And that's going to also be true when we take a look at the generator today. Okay? Okay. Now, I want to take a look at the generator here. The book has a diagram of a generator. Let's see if we can make that diagram a little bit smaller so we can see the whole thing. There we go. Now, here's how a generator functions. First of all, I want you to understand the concept, and then we'll come back and we'll generate an equation for it. And I'm going to take a slightly different approach because I'm going to assume that you're not fully and totally allergic to calculus. So, the concept behind the generator is that we have this wire loop here. And this is simplified because in real life we would actually use many wire loops so we can get that n multiplier in our equation. I'm going to take this wire loop and we're now going to rotate it like this by means of some kind of heat engine, or Superman turning it with a crank, or, you know, butter toast strapped to the back of cats, what have you. That's a joke. Do you understand the joke? Oh, so the thing is that butter toast is always supposed to land buttered side down, and cats are always supposed to land on their feet. So if you strap butter toast to the back of a cat and drop it, theoretically it should just spin. Right? And then you attach it to a wire loop and put it into a magnetic field and free power forever. Yeah. Yeah, there's only one flaw with that plan. Cats are allergic to butter. No, I'm kidding. So in any event, what happens now is we have these 4 different pieces of wire that are making up this loop. And the 2 pieces of wire here and here are cutting through the magnetic field, but as they do so, they have no area associated with them because the field is going in this direction, and the pieces of wire are like this. And as they spin in the field, they're simply spinning parallel to the field. They're not spinning across any field lines in the across the direction of the field. So these guys will contribute nothing to the EMF. Agreed. But the ones in blue, here and here, are now going to cut through the field lines as they come around. You can see my finger here representing field lines, and again, draw it forward. So as the loop turns, this piece of wire is going to cut through the field lines, and as it cuts through, it's going to experience EMF, just like that Hall effect that we saw earlier. So we're going to end up with one side that's plus and one side that's minus, and because these guys are moving in opposite directions, you're going to end up with opposite signs here. So if this is plus and this is minus, then this guy's going to end up being minus and that's going to be plus, and it's all going to push current in one direction, like so. And in fact, these will basically be like 2 batteries stacked together. Okay? Now, your book goes through a fairly complicated derivation using geometry, trig, to generate the equation. I would like to do it in a more simple fashion using a little bit of calculus, but I need to explain. So let's start with Faraday's law of induction. And that is that the EMF that's generated should be equal to negative n times the rate of change of the flux. And then I want to remind you that the flux in general is equal to V times A times the cosine of the angle between the normal vector. Here comes my area vector or normal vector right here, and it's going to make an angle theta with the magnetic field like that, so that I have maximum flux when my wire loop is straight up and down, so that theta is 0, cosine of 0 is 1, and I have 0 flux when my wire loop is like this, and my angle theta is 90 degrees, and the cosine of 90 degrees is 0. Okay? So all that we have to do is to figure out what happens here with this rate of change. That's going to be our task. And we observe that this situation is different from the other 2. In the case of the metal bar going across, the area was changing. In the case of the changing magnetic field, the area was constant, but the field was changing. Now the field remains constant, and the area remains constant, but the angle is changing as the generator turns. So we have to figure out how cosine theta changes as the angle changes. And that's really a calculus function. So I'm going to develop that just a little bit. Okay. But before I do that, observe that if we are rotating at a constant speed, which makes a whole lot of sense, you don't want to have something fancy that speeds up and slows down, you want it to just rotate at a constant speed. So if we have a constant rotational speed, then theta is simply going to be the angular speed omega times time. So that for the generator, flux is going to be equal to B times A times cosine omega t. And that's the flux, that's not the EMF. The EMF is going to be the rate of change of this flux. Right.
Where did we get the WT from?
It's omega t, and that is, remember all the way back when we did rotational motion, right? And so this is the rate, or the rate of change, or the rotational speed. And if we assume that it's constant, then the amount of angle that we travel is just speed times time. Okay.
Where did they go?
There at the APUS.
Oh,
Okay, so our job is to figure out the rate of change of this guy. And I'm now going to go over to and develop a kind of calculus idea. If we take a look, in fact, let me do this calculus, because it'll be more evident that way. If we take a look at the graph of cosine, then when we talk about rate of change, we're talking about a slope. And so what we're going to do is we're going to use the graph of cosine to figure out the slope at different points. And we're going to plot that slope and just observe what it looks like. So, if I set y equal to cosine x, and let's do a suitable window size. Let's go, how about negative 2 pi to positive 2 pi? That'll take us through 2 periods of cosine. And now, because cosine has an amplitude of 1, then I'm going to make my y window size be negative 2 to 2. And we will graph that guy and see what we see. Very familiar graph, right? Okay. Now what we'd like to do is we'd like to identify the slope at various points here. And it's fairly clear that if I draw myself a tangent line right here to get the slope at this point, then I have slope of 0 at the maxes and mins. That's going to be a slope of 0 at 0, pi, 2 pi, negative pi, and negative 2 pi. So already we have 5 points on our graph of the slope. And I'll mark those points here, 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 here. Okay. Then, if I go to some other points, maybe I'll go to the points where the curve is the steepest. And it looks to me like my curve gets the steepest right here, and then the steepest downhill right there. See what I'm saying? So my curve turns upwards. It's not very steep here, but becomes very steep right there. And when I actually compute the slope right here, and if I were doing this on graph paper, I could compute the slope more easily, I would actually find that the slope right here is equal to positive 1, which is interesting. So that would give me now some different points. Let me do this in green so we can go compare and contrast. And this is right where the curve goes, the cosine curve goes through the axis. That's at negative pi over 2. So that at negative pi over 2, right at this point, my slope is positive 1. And right here at positive pi over 2, my slope is negative 1. Right there. And then it repeats itself, so we have a slope of positive 1 here, and we have a slope of negative 1 here. Is everybody with me on the slopes? Okay. And now if I just connect the dots with a smooth curve, because it looks to me like cosine is smooth, and therefore it makes sense that its slope would also be a continuous curve, then what I find is that the graph of the slope looks like this. Whoa, that looks like a familiar trig function, almost. It looks just like the graph of sine x, except that it's upside down. Sine x starts at 0, goes up to 1, and then back down. I take this whole graph and I flip it. So what this strongly suggests to us is that if y equals cosine of theta, then the rate at which y changes with respect to theta, notice I didn't say with respect to time then, is going to be equal to negative theta. This is the calculus idea that I figured that you guys were brave enough to handle. And if you have been in calculus, then you recognize a derivative right away. That in fact, I can use a little bit of limit foo to prove that this result is exactly correct. So if you'll take that as a given, and it certainly does seem plausible based on the graph here examining the slopes. If you'll take this as a given, now we can modify it to ask, well, what if y is equal to cosine of omega t, which is what we have over in our flux equation. Then what would the rate of change of y with respect to time t be? So, to get at that, I want to appeal to an idea that you learned from Miss John, which is, if I multiply on the inside by omega, what does that do to my graph? If the graph of cosine has a period of 2 pi like this, and then I multiply the inside by omega, what's going to happen to my graph? Yes, it's going to be a compression by a factor of omega. So everything is going to squish this way. It's not going to get any taller. It's going to squish this way. Now just reason with me. If I take the graph of cosine, so this is y equals cosine of t, and then I squish it by, let's say, a factor of 2, something like this, y equals cosine, y2 equals cosine of 2t, and I take a look at the slopes, then what I find is this. I'm going to go up by the same amount, but I'm going to do it in half the distance. So that, in general, when I squish by a factor of omega, all of my slopes get slopier by that same factor of omega. So that delta y over delta t will be negative sine omega t like we had here, but it's going to be multiplied by a factor of omega because I'm swishing the graph in the x direction, the t direction, really, in the t direction by a factor of omega, causing all of my tangent lines to squish along with them. And lo and behold, in one fell swoop, I've just taught you 2 big ideas in calculus. The derivative of cosine and the chain.
Is you maintenance will be expanded omega is less than 1?
Yes, if omega, that's a great point. If omega is less than 1, which does not happen with our generator, because that would mean that we are turning really slowly. But it, it might happen if we had some massive generator out there that can only turn really slowly. But if omega is less than 1, notice that we actually get a now rate of change that is slower than sine omega t, because with an omega less than 1, I'm actually expanding my graph and making my slopes even lower because my tangent lines are also expanding in the t direction. Yes. So this relation works for omegas that are both greater than 1 and less than 1 and equal to 1 even. All right. So with all of that in mind, we now have a powerful way to come back and evaluate the EMF directly. And that is that since the flux is BA cosine omega t, therefore the rate of change of flux is going to be equal to the rate of change of BA cosine omega t. And because B and A are constant, not changing, I can just factor them out of that change, so that what I end up with is the rate of change of just the cosine omega t, and that's exactly what we did on the other page. That is equal to negative BA omega sine omega t. And if we now plug this into Faraday's law of induction, EMF equals negative n times change in flux over change in time. Substituting this guy right into here, I get positive n, negative times nu, times B A omega sine omega t. And this is our generator equation, Grant, that you were asking about earlier. This is where it comes from. And it has some really interesting implications for us, which leads to a food fight between Tesla and Edison.
Isn't that where they decided that direct current
Should not be used, right? And there were a couple of reasons for that. This was one of them.
Didn't Tesla use the direct current so that we would... Didn't he make something with direct current so that they wouldn't use direct current or something?
Tesla was a fan of using direct current. Edison,
Yeah, didn't he make the electric chair?
I don't know.
Someone made the electric chair and that's why they didn't use direct current.
I don't know about that. Electric chairs would probably work with either one. Okay. So, here are the implications of this. The first implication is this. The faster that I turn my generator, the larger omega is going to be. And as a result, the larger the EMF is going to be. Now, think about those hand generators that you've seen. Have you seen those hand generators where you turn the crank and the light bulb lights up or whatever? How does it work? The faster you turn, the brighter the light gets. Why? Because you're generating more EMF. Ta-da! That's it. That's the first thing. The second implication is that I can increase my EMF with the rotational speed. I can also increase it by increasing any one of these factors. So the more coils that I have around my generator, the more effective it's going to be. Now you can see why we use a lot of coils. If I have a choice, if I want to double my EMF and I have a choice between 2 times as many coils or twice rotating it twice as fast, I know which one I'm going to pick. Exactly. I can also do it better, get more EMF, if I use a larger area. In other words, these things work better on industrial scales, such as having a humongous generator inside a hydroelectric dam, so that the water going through causes the whole thing to turn at a rapid rate of speed. Okay. Now, so the first implication then is that I can increase EMF with increase in any factor, N, B, A, or omega. The second implication is that the EMF that is generated is not going to be a constant, but instead is going to be a sinusoidal function of time. In other words, we call this an alternating current. EMF generated will be AC, not DC, from the generator. two major reasons that the alternating current wins the fight during the early stages of American electricity infrastructure. What it means when I say that this will be alternating current is that when you take a look at a graph of the voltage versus time that's coming out of your wall socket or coming out of the generator, that voltage versus time is going to be varying very quickly. It will be alternating back and forth between plus and minus. So whereas, so this is alternating current, or AC, and we contrast that with the very boring direct current, or DC, that has been coming out of your power supplies in the lab that looks just like that. So I want to be clear about what's happening with your wall socket. With your wall socket, you've got two plugs. You actually have three. Okay. And the two plugs are actually not the same size. The one on the left is actually a little bit larger. And this guy right here is called the neutral, the large one. And it is connected to the ground. And this guy right here is called hot. The active, or there's several other terms that are used right here. And it is this hot one right here that is going to experience the time varying voltage that you see. It is going to alternate between positive and negative. And specifically, it is going to, quick calculation here, it's going to alternate between plus and minus 165 volts in the United States. In Europe, it's actually a larger number. In Europe, it's going to alternate between 300, plus or minus 300 volts, which is humongous. I mean, you think about what we've been doing in the lab, we've been doing stuff with like 13 volts. This is more than 10 times that. In Europe, you're going to have more than 20 times that.
And that's why I shock yourself with the key.
Right. That's exactly why you do not want to stick metal stuff into the outlet. Now, so this is kind of strange, because with the DC power supplies we've been using, you have a plus side and you have a minus side, and current flows from plus and minus. Things are not like that with the with your wall socket right here. With your wall socket, what's going to happen is that because you have alternating voltage going from plus to minus, like so, that means that during the plus side of the cycle, current is going to flow this way. And during the minus side of the cycle, the current is going to flow back this way. So instead of current going through wires like it does for DC, your current is going to alternate from forward and backwards. And it's going to do it every time there is a cycle. Well, how quickly are the cycles? That also depends on what country you're in. If you're in the United States, the frequency for alternating current is 60 hertz, or 60 cycles per second. That means that the period here of one cycle is going to be 1/60th of a second, which is very, very fast. That means that the alternating is not like this, boom, boom, but like this. Yeah, and even faster than understood. It's going to be alternating back and forth like that. And when you hear the low-pitched hum of power wires. Have you ever walked underneath power wires? That's actually a frequency of either 60 or maybe 120 hertz, the harmonic on the top of it. Okay, So the things to understand about alternating current, it's going to alternate back and forth. It's going to do it very quickly. If you're in Europe, the frequency is 50 hertz. And that's why if you go from the United States to Europe and you carry any electronic equipment with you, carry an adapter. That adapter is going to transform the voltage to the right level, amplitude-wise. It's actually also going to change the frequency. There's some sophisticated electronics in there that actually take 60 hertz and scale it down to 50. Okay. So, the second reason, by the way, we will get to next week, and the second reason that AC wins out over DC is that it turns out that a transformer, which is the component that we'll look at next week, is easily able to take AC at one voltage level and turn it to AC at another voltage level, so that you can transmit. The high wires are going to be something like 150 kilovolts, but very low current, and then it's going to step down to, by the time it gets to your house, 120 volts at a much higher current. Speaking of 120 volts, what did I mean by that? Well, I want you to notice one more thing about AC, and that is that because the AC starts at 0, goes up to its maximum at 165, back to 0, back to minus 165, that it's a little hard to say what the voltage is at any given instant in time, right? So if you wanted to know how much power am I getting out of this thing right here, you'd need some kind of average. But the average that you need is not the average of the voltage itself, which is 0, because you have just as much minus as you have plus. Instead, what you're interested in is the average amount of power, or V squared over R, that's being delivered. And so the average power is proportional to the square of the voltage. And it turns out that when you have a sine wave or a cosine wave, and you do a little bit of calculus with it, then the average of the square of that sine wave or cosine wave, take average value of cosine squared, right, integral of, blah, 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 then what you get is the maximum divided by root 2. This is called the RMS, or root mean square average. And if you want to know the official way to calculate it, I'll put this up here, just for those of you who know calculus. Then it's going to be equal to 1 over the period times the integral from 0 to the period of a cosine negative t squared, and all of that square rooted.
So that's the same as.
Yes. Now, when we actually use this formula, you don't need to use this formula to calculate it here. When we actually calculate the RMS voltage, what we get is 117 volts, which rounds to 120. So we usually say that what's coming out of the wall is 120. It isn't really 120. It has an amplitude of 165, and it oscillates back and forth. But on average, it generates as much power as if it were DC at 120.
Out of curiosity, Mr. Cable, what is the bottom of that outlet?
Oh, yes. So the bottom of that outlet is ground connected to your house ground, rather than ground connected all the way back to the power station ground. And the purpose of that is to provide protection against surges, essentially.
And so some courts don't have it, and some do.
Exactly.
The one that do, like,
It's actually for extra protection against surges. So what can happen is this. Ground is a funny thing because we think of it as zero, but really it's relative to wherever zero is. So if you have two electrical appliances that are both, quote, grounded, but they are grounded to different grounds, they can actually be many volts apart from each other. In fact, I had the experience once of playing the electric guitar with a friend of mine. We both had our guitars plugged into amps, and I had my guitar plugged into my amp, and I sat down on his amp, and I got shocked. And I got up, and I did it again, thinking, maybe it was just static, and I could feel a buzz through the seat of my pants. And the reason was really simple. My electric guitar had, if you know what quarter-inch cables look like, the tip is the hot, and then the shaft right there is the ground. And so I was plugged into ground on my amp. His amp was grounded, and for whatever reason, the ground was at a different level. Obviously more than 40 volts difference, because that's the threshold of being able to feel it. And so I sat on that and was essentially a conducting current through my rear end. So the bottom line is that if, for whatever reason, the power station ground here were to be not at zero relative to the stuff in your house, then you could actually get significantly shocked. So this actually ties into the ground in your house. In other words, the pieces of metal, some large piece of metal in your house, to ensure that 120 will be 120 and not something much larger. DCFI is a little bit different. The outlets that have the red button on them,
Yeah.
and I'll explain those another
Yeah,
time.
push that off.
Yes, that rose toy.
No, it's that button.